we need a way of putting electrons into atoms and representing that, because we were doing that, or we need to do that in order to understand bonding and some atomic properties as well. So this is what we used to do before, but that model of the atom has been replaced, so we can't use that anymore. So we need to figure out how to do that with quantum theory. So with quantum theory, of course, we're having orbitals, which are areas of probability, or perhaps volume of probability. And the problem with drawing an orbital is the orbital comes from this notion of a whole bunch of little dots. No, you don't have to draw that. And then there are different orientations for these boxes, or these orbitals. So we need to be able to represent all of that. And then electrons have spin, and we can have a couple of different possibilities for spin, and we're going to pair up electrons with opposite spins. So we need a way of representing that. And the other thing is, one of the things that we've recognized or learned is that within an orbital you can fit a maximum of 2 electrons. They'll have exactly the same quantum numbers. The only difference is one of them will be a plus 1/2 spin, the other a minus 1/2 spin. And then after that you need more orbitals. So we're going to use a box to put our electrons in, and that's how I'm going to represent an orbital. I've seen circles, but I'm going to use boxes. Sometimes I have one box, well, sometimes I have multiple boxes, and we'll talk about how we know what to do in a minute. But we've talked about energy levels and sub-energy levels. So sub-energy levels come down to these sets of boxes. How many boxes do I have? 1, 3, something else. Okay, if we're going to fill an orbital box, put electrons in it, I'm going to represent an electron using an arrow, either pointing up or pointing down. So an orbital with 1 electron is going to be an arrow pointing up. If I have a second electron, you guessed it, arrow pointing down. How do I know how to fill that, the order that I use? Well, that comes down to these 2 basic rules. One of them is that you're going to half fill a set of orbitals, and then you'll fully fill it. So in my first one there, that single box represents, it's a pretty small set, but a set. So I'm going to half fill it, and then I'm going to fully fill it. After that, I'm going to move on to the next set, and I'm going to half fill that set, and then I will fully fill that set. So in other words, I'm going to put 1 electron in the first box, and then I'll put 1 electron in the next box, and then I'll put another electron in the third box before I go back and start to fully fill that set of orbitals. Okay, how do I know which kind of, or how many boxes to draw and how the order of filling? Well, we're going to work on that one next. Okay, starting with how many boxes. It comes down to the number of orientations that you're allowed to have. And the number of orientations that you have comes down to the number of m sub L values that there are. So if you think about your listing out your quantum numbers, so you've got n equals 3, for example. L can be 0, 1, or 2, and I know we don't normally write them out that far apart, and that's okay. We're going to be using it to draw boxes. The next line, you would never be asked to write it out like this when you're listing quantum numbers. If you're asked to list quantum numbers, you just do what we've done before. You'll notice here, though, a couple of numbers get reused as we go, each time around. So when you're asked to list quantum numbers, just the list. You don't have to break it out like that. Okay, for each value of m sub L, I need an orbital, because that's a different orientation. There are some, however, that are coming from the different sub-energy levels. They're all coming from different sub-energy levels. And so I'm going to draw boxes based on the number of m sub L values. One m sub L value, 1 box. 5 m sub L values, 5 boxes, where each box represents an orbital within a particular orientation. Okay. Also, I'm going to, as I eventually get beyond just doing this, I'm going to be identifying these things with letter designations that correspond to the value of L. So in that middle set, L is equal to 1. That corresponds to a p-type orbital. And the 3, of course, is the energy level that it's in. Okay, so that's just getting a little bit of a peek ahead at some things coming up. Okay, we're going to fill some atoms. So we're going to start with hydrogen, because it's the easiest one, 1 electron. That 1 electron is in the first energy level, and the quantum numbers would be this. N equals 1, L equals 0, M sub L equals 0, And for hydrogen, I'm going to arbitrarily decide that it has an electron spinning plus 1/2. It could be spinning minus 1/2, but it doesn't really matter for what we're doing. So I need one box. I need one electron in that box, and I'm going to put the arrow pointing up. As I move on to helium, well, I'm going to have 2 electrons. Both of them are in the first energy level, and the quantum numbers for the first electron are going to be exactly the same as quantum numbers for the first electron in hydrogen, but the second electron will have almost exactly the same quantum numbers. The exception will be the spin, so that I can pair up my electrons in that orbital with different quantum numbers. One difference in the quantum number, and that difference will be the spin. Okay. As I move on to other ones, what's going to happen is that I'm going to fill them from the bottom up and move on to the next one. Now, once I move on to n equals 2, I've got a couple of different possibilities for L. So I'm going to start with the lowest and work my way up. So, keeping in mind those 2 rules from earlier, if I had a second energy level, then I've got basically the same kind of thing. N equals 2, L equals 0, M sub L equals 0. It's going to look like the first one. N equals 2, L equals 1, M sub L equals -1, 0, and 1. And then I could fill that. Okay. But to actually figure out the electrons for the next row, starting with, say, beryllium, element number 3, sorry, lithium, element number 3, it also has the first energy level. So the first 2 electrons in lithium are going to go into the same places as the first 2 electrons in helium. The third electron moves on to the next one up. Beryllium, element number 4, is going to start doing exactly the same thing that lithium did, and then it's going to add that next electron, electron number 4, which is going to pair up in that first box. After that, element number 5, or electron number 5, boron, it's going to start filling from the bottom up. It's going to put the first 4 electrons where beryllium put them. Electron number 5 is going to go into the next available box. Now, realistically, all of those orbitals in that group of 3 are identical, so it could go anywhere, but by convention, by habit, we do it like this. We just start from the left and move to the right. Carbon, element number 6, 6 electrons. The first 5 are going to go in exactly the same place. Electron number 6, I want to half fill that set, and then I fully fill it. So it goes into its own box. Okay? And that's really all there is to it. Now, I shouldn't quite say it that way, because if I gave you any element on the periodic table and asked you to write the orbital box diagram for it, you might have to start from scratch, and we don't want to do that. We want to be able to have a way of predicting and writing orbital box diagrams or drawing orbital box diagrams without starting from hydrogen every time. We also want to have some notation for it so that we're not always drawing orbital box diagrams. And then we want to be able to use those orbital box diagrams to describe or explain properties. Why does it bond that way? Why does it have these other properties going on with it? So those are the kinds of things that we want to be able to do. It's what we were doing with Bohr diagrams from back in the day. Okay? So pretty much that's what we're looking at, and that's what we've done. Okay? And if you can do that, you're golden. Talk to you another time.